Okay, let's go ahead and get started. Welcome everyone to our GIA Knowledge Sessions. These are a series of talks and seminars about gemology that are fueled by our decades of research. And it's our mission to share all of our discoveries and learnings with the world. So I'm very excited to kick things off today. I'm Kelly Giordano, a member of the content team here at GIA, and I'm joined by Dr. Wuyi Wang, Vice President of Research and Development at GIA. And he's going to tell us all about diamond color treatment and how to detect it. So before we get started, just a bit of housekeeping. Everyone attending this is automatically muted, but if you have a question, please submit it using the Q&A feature at the bottom of your screen, and feel free to ask questions as we go. There will be a Q&A session at the end where Dr. Wang will be able to answer some of your questions. We'll also send a recording of this session to you either later today or early tomorrow morning. That email will also have a survey, so we'd love to hear your feedback. And with that, I'm going to pass you over to Wuyi.
Thank you, Katie. Thank you, everybody, for attending this presentation. Okay, today I would like to take this opportunity to talk about the diamond color treatment and its identification. How do we identify a treated diamond in the laboratory, like in GIA? Color is a very important feature of a gem diamond. GIA in 1950s set up the D to Z diamond color grading system, and then in 1990s set up the color grading system for fancy colored diamond. What I'm showing here is just a few diamonds actually auctioned in an auction house. They show the top colorness or some very attractive fancy colors. Of course, they claimed they're all natural diamond. They claimed a very high value in the market. One of the reasons is this diamond of this color are very, very rare. And it is very, in particular for this fancy color diamond, as you can see, if you calculate the carat price, the fancy color diamond, or is a naturally colored diamond, it's a much higher value than the colorless ones. It is a very easy to imagine to implement, to develop a treatment method to improve the color of natural diamond. So color like this, either top colorness or fancy color, can be introduced to more diamond. So in this presentation, I'm going to cover the color of diamond, why diamond could have colors, and then to review the major treatment method, and then talk about some principles in laboratory, how we separate naturally colored diamond from a treated diamond. So we know diamond is a very simple mineral. It is composed of a carbon only. In this diagram, I just used a simplified crystal structure of diamond. As you can see here, every carbon atom stay where it's supposed to stay, nothing missed, there's no impurities. So basically we call this a perfect diamond. A perfect diamond that has no defect is colorless. Simple. A perfect diamond is colorless. But if some carbon atoms are replaced, for example, by boron here, the blue dot here is replaced by boron, the diamond could show a blue color. And if carbon atoms are replaced by nitrogen, what I'm talking here is the isotope nitrogen. One nitrogen replace another carbon, the diamond could show potentially yellow color. As we see some beautiful yellow color, either naturally yellow, not all of them, but in particular for some HPHD synthetic yellow diamond, that's due to this isolated nitrogen atoms. If one carbon atom is missed for whatever reason, so what I show here is one carbon atom is missed and is referred as a vacancy in diamond. A vacancy in diamond could introduce blue color. Now, interesting saying, if a vacancy is side by side with a nitrogen called NV centers, now the diamond could turn to pink. So very recently, element 6, Dr. Daniel Tutichin gave a very impressive talk about the quantum CVD synthetic diamond with the MV centers. That's what the defect is. And of course, the diamond with a beautiful pink color and have a great potential application in quantum science. So with a very simple review, we know a perfect diamond is a colorless. It doesn't necessarily mean a colorless diamond is a perfect. There's no perfect diamond in the world. All diamonds will have some defects, either could be some impurities or anything else. But anyway, a perfect diamond is a colorless. But diamond always contain some defects. It could be impurities, like different atoms getting into the diamond lattice, could be vacancy clusters and interstitials, could be deformation and their combinations. So diamond is a natural synthetic, could have many types of defects. Some defects, not all defects, some defects could selectively absorb visible light. So defects could interact with a light. What I try to emphasize here, they could selectively absorb only a range of visible light. We know visible light has a pretty big range. I will show more later. But if a small range is selectively absorbed, and then potentially we'll be able to see a fancy color. Of course, the concentration is important. We need to have enough defects, then diamond will show the fancy colors. Diamond has many types of defects, more than what we could know how many defects they have, but the impact, the potential impact to the color of a diamond, the defect numbers, is quite limited. Here, what I try to show first is the human eyes can see the range from about 400 nanometers to about 700 nanometers is range. That's what we see as a visible light. And what I show here are the major defects that selectively absorb a range of visible light. For example, if I use this NV neutral and NV negative defect here, they absorb basically everything from green, yellow, orange. They absorb this whole range, and then the diamond will have a red area that's transparent. Basically, red light would be able to go through the diamond. That's why we see a diamond could show red color, or if the concentration is low, that could be a pink color. That's how it works to create a color in a diamond. Here I'm going to show you some basic principles, concept of color of a diamond. Here what I try to show is two very famous blue diamond due to boron impurity. One is the Widowsburg graph, this diamond. Another one is a Hope diamond collected in the Smithsonian Institute. Both are type 2B, colored by trace amount of boron. What I try to emphasize here, diamond just need very little impurity to introduce quite a lot of color. For example, in these two diamonds, the boron concentration is only about 0.2 to 0.4 ppm. That's a parts per million. So it's very low concentration of impurities would be able to introduce quite a lot of color in a diamond. So this is the first thing I want to emphasize. Second thing, what I try to show here, the three diamond with a brown with a brown color. The left-hand side is a light brown, quite intense at the middle. And when the brown is so intense, the diamond even show basically black color. Brown color is very common in natural diamonds, and it is not so attractive. It really decrease the value of a diamond in the market. After many years research, finally we got to know the brown color is due to a defect called vacancy cluster. So what I try to show here, the concept is the darkness of a color is proportional to the concentration of the defect in a diamond. If for a specific color, if the concentration of a defect is very high, it will be in darker. So since brown color is so common and so important when we talk about treatment, I will mention a little bit about the brown color is also very common in CVD synthetics. We grow CVD reasonably fast and have some brown color, and that brown color, we still don't know for sure that's due to vacancy cluster or not. That could be different from color region of a natural diamond. One more thing I want to talk about the color of a diamond is a similar color. For example, I show here two pink diamonds. Both are pink, and similar color could be attributed to different defects. Diamond could have many types of defects. And the stone in the left, actually this is a pink diamond from an Argyle diamond mine, is colored by a defect, what we call the 550 nanometer band. And Argyle pink diamond is exclusively due to this defect, 550 band, that gives the pink color. But the stone at the right-hand side is a similar color, but it's due to NV center. So the concept is a similar color of a diamond could be attributed to different defects. That is very true for yellow diamonds. There are many, probably close to 10 types of defects that could introduce yellow color or orange color in a diamond. Well, we studied diamond defects for a very long time because diamond is such an important material, not only to our jewelry industry, but also very important material for other industries. So we studied diamond for a long time, even though there's still a lot we don't know. For example, this is a very special diamond that show bluish, basically is a violet color. And this is probably the largest violet color from the Argyle mine. And what is responsible for the color of the diamond? Actually, we still don't know exactly what it is. And GIA, actually, currently we have a postdoctor in GIA, Dr. Chloe Beaker. This is her project try to figure out from a theoretical viewpoint what defect could be responsible for this type of a very special color. So there are a lot of things we don't know about color of diamond. Another thing is another example is a very well-known chameleon diamond. The color is not stable; it changes. What I show here is at the top is a chameleon diamond. A stable color shows type of yellowish, brownish, green body color. This is a stable color at room temperature. When this diamond is heated by alcohol lamp, for example, to a few hundred degrees C, it turned to beautiful, vivid, very bright yellow-orange color. But when the temperature drops, with the time, the color restored back to this original stable color like greenish yellow, yellowish green color. This is called thermochromic feature. When you heat a diamond, the color become changed. And for the same chameleon diamond, we put the diamond in dark, and we are very lucky. We were able to put this diamond in dark for 48 days. After 48 days, the diamond turned to yellow color, very similar orange color, similar after heating, and then when the exposure to room light, it gradually restored to its stable yellowish green color. So anyway, what I try to show here, the color is a very important feature of a diamond, and something we know, there are quite a lot we still don't know. For natural diamonds, of course, it's very well known for the colorless ones, but diamond could be any color, could be as colorful as colored stones, ruby, sapphires, emerald, could be any color. But the top gem quality diamonds, either colorless or attractive fancy colors, these stones are very rare. So here's basically a very simplified diagram to show the market value of gem diamond. When diamond color getting lighter, go to the D color, for example, the value increases. On the other hand, on the side, if the color getting darker and be some attractive fancy colors, the value increase much more in the market. Both these top colorless or top fancy color diamonds are very rare in natural among natural stones. So it is very reasonable to believe, very natural to say take different type of technologies will be developed to improve the color of this type of diamond, to either make it lighter or get it darker to increase their market value. So how do we change the color of a diamond? In principle, technically we're talking here about a permanent color change. We're not talking about a coating. We're not discussing anything like a coating or fresh filling. We're talking about a permanent change the color of diamond related to the diamond lattice in this presentation. So 3 different ways. One is to introduce desired defects, because now we know diamond has color because diamond has defects, have a lattice defect. So we can introduce the defects we like, introduce the color we want with a suitable concentration. Of course, that's very important. We don't want to be too dark or too light. And also the distribution is important. We want the color to be evenly, or as much as possible, to be evenly distributed. Or we remove the defects that we don't like the brown color. It's due to vacancy clusters. There a technique we can remove the vacancy clusters to reduce the brown color, so to remove the unwanted defects, or combination of both. So that will give us more options. We remove the defects we don't want and to add in the defect we like. So that's basically the principles for diamond color treatment. Over almost a century, a history of diamond treatment, and there are probably 3 major technologies we still are using to improve color of diamond. So first one has been a long history, started almost a century ago, is irradiation with or without annealing. So we put a diamond at a very high energy beam and to be irradiated, and some stone could be heated after the irradiation. Some may not necessarily be heated, depends on what color we want. The second technology is HPHD annealing, so high pressure and high temperature annealing. So what we talk here has nothing to do with the growth. It is to put a diamond, either natural diamond or synthetic diamond, at a high pressure, high temperature, to change it, to modify, to change its color. Then it's just a combination of these 2 technologies, and we call it multiple treatment. So from here, I'm going to review what this technology can achieve in terms of a change color of a diamond. For irradiation treatment, the high energy beam, mainly the electron beam, is frequently used. And in addition to electron beam, there's still a neutron beam and a gamma ray. And electron beam has a lot of advantages comparing with the neutron and the gamma ray treatment. So I think it's almost exclusively in the diamond industry right now. The treatment, when we talk about irradiation, the stones, the diamonds are irradiated with the electrons, and its facility is quite easy to locate all over the world. So here are the major. This slide I try to show you the major color could be introduced using the irradiation treatment technology. The irradiation treatment itself, without heating, basically introduces a vacancy. We taught at the beginning the vacancy would introduce a blue color. So this is basically a blue color introduced by the irradiation. If a diamond has some brown color or yellow color, after the irradiation will turn to green. Basically, it is a yellow plus blue, that means green color. So these 2 stones at the left-hand side, just irradiation only without any annealing. But if a diamond, we're talking basically here, type 1A diamond, after irradiation, these stones are heated up, the 2 type of defects, H3, H4, will be introduced that can generate yellow, some orange or brown color. And sometimes depends if the H3 defects of fluorescence can contribute to green color. And for a small group of stones, if heated to a very high temperature, a strong H2 defect, a high concentration H2 defect could be introduced that could create another type of a little bit kind of green, but not so bright green comparing with this green due to H3 fluorescence. If a natural diamond has a little bit of isolated nitrogen, and this stone irradiated and annealed, NV center will be introduced. That will turn stone to pink or red, depends on the concentration of isolated nitrogen and also the treatment conditions. I just want to point out that natural diamond with a suitable concentration for isolated nitrogen is very, very rare. So the material suitable for, natural material suitable for turning to pink is not so easy to find. Just some brief summary of features of irradiation treatment. This technology is very effective. The cost is very low to change color of a diamond. But if we say some disadvantage of technology is this technology doesn't remove pre-existing color. It basically just add additional color to the diamond. Whatever exists there, it will stay. So basically it's add a layer of a mask to improve the color of the diamond. So this is the first thing. Second thing, the final color, whatever it turns out to be, will heavily rely upon the features of the starting material, basically the chemistry of the starting material. For any treatment, any gemstone treatment is a similar same. It's just a matter of how much it relies upon the original chemistry of the starting material to be treated. For HPHD annealing, we know in this diagram, which I try to show the phase diagram of a carbon. The graphite stable region is the pressure and the temperature, and the diamond stable region. We know natural diamond basically is formed in about 1,000 to 1,200 degrees C, about a 5 GPa. This natural diamond formed, most of natural diamond formed at about this condition. For HPHD treatment, they maintain similar pressure, about 5 to 6 GPa, but temperature increased much higher to 2,000 degrees C or sometimes 2,200 degrees C for a short period of time. At such a high temperature, diamond mostly stay in the diamond stable region or a little bit in the graphite stable region for a short period of time. The defects in diamond will start a chemical reaction. Some defects can be removed in a very short period of time, or some defects could be introduced very, very quickly, as to how the color change could be introduced. I'll just show you an example here. This is the diamond treatment we did in GIA. A very large 2A boron diamond we purchased, laser cut in 2 halves, and then just to go through the polishing. When fully polished, it's a beautiful brown color. After HPHD treatment, as you can see, the brown color is entirely removed. Surface a little bit frosted, as you can imagine, because diamond was stayed at a very high temperature. And then after repolishing, that just loses very, very little of the stone from turn out to be a beautiful colorless diamond. So I'll show you how effective the HPHD treatment could be in change the color of a type 2A diamond. And here I want to show you more examples and how HPHD treatment could change the color of a diamond. The top row diamond is a natural color, and the lower row is after treatment. So before and after treatment, the brown 2A turn to colorless, and sometimes brown 2A, if treated at a slightly lower temperature, could turn to pink color. And a gray type 2B diamond, this is the type 2B diamond, will turn to a beautiful blue color. The gray color will be removed. So here we just want to show that HPHD treatment is very effective in change color of type 2 diamond. And of course, similar to irradiation treatment, the final result will be heavily rely upon the starting material chemistry. It is almost impossible to turn a gray color diamond after HPHD turn to pink, or same thing for a brown color, almost impossible after the treatment to turn them to blue color. It is the final color is heavily rely upon the starting material chemistry. For type 1A diamond, a slightly colored yellow diamond could turn to very intense yellow because the acid nitrogen could be introduced after HPHD treatment. And a brown color could turn to greenish yellow, yellowish green, basically due to the fluorescence of the H3 defect that is introduced due to treatment. Some gray color natural diamond could turn to beautiful orange color. This is for type 1A diamond. So in the laboratory, in GIA, these are just some examples of a diamond after HPHD treatment we identified. These stones are all submitted without any disclosure. And as you can see, for type 2A diamond, some of them up to 38, close to 40 carats. This amazing technology can treat a diamond of this size to decolorize it. Some show beautiful pink, like this one, 23.8 color pink diamond. If these stones, these 2B diamonds, were naturally colored in the auction house, I would believe they would go higher than $1 million per carat for a diamond with this type of a color. Most HPHD treated stones we detected in GI laboratory are type 2 diamond, but occasionally we also see some type 1A diamond treated. For example, here, this is a type 1A, it's over 28 carat after being treated. So we talked about the irradiation treatment and HPHD treatment, and both the HPHD technology have a huge advantage over irradiation is this technology can remove some color that we don't like. That is very different from irradiation. Irradiation doesn't remove pre-existing, but HPHD treatment can, but that is very limited. It's remove a brown color, and also the final result is heavily rely upon the starting material chemistry. So both technologies have some limitations. So of course, it's very easy to say, why don't we use the two technologies to combine these two technologies to create more opportunities, more options. So that's the multiple treatment. The multiple treatments just take advantage of irradiation annealing as well as HPHD treatment to design the best method to reach the best color. So what I try to show here is if we have a brown color diamond, for example, either type 1A or type 2A, if the type 2A after HPH treatment, the brown color will be removed. But if 1A, brown color will be removed, and it may introduce a little bit of acid nitrogen. And this stone could be colorless and near colorless, or very slightly yellow color, but immediately after HPH treatment. If these stones are irradiated, it could turn to beautiful blue like this color, or turn to some green color. Now we know if acid nitrogen is introduced with suitable concentration. I try to emphasize how important it is with a suitable concentration of acid nitrogen. If this stone is irradiated and annealed, MV center will be introduced, and depends on the MV center concentration, a diamond could be lightly colored pink. I mean, pink very popular in the trade, or the stone could turn to red color. We know natural diamond with a fancy red color grading is very limited. It's probably, I don't know exact number. It could be less than 20 stones in the whole world. But with this type of multiple treatment, HPHD plus irradiation annealing, we can turn many natural diamond to red color. The treatment not only apply to natural diamonds, it can also be applied to synthetic, and I just try to mix the term synthetic or lab-grown diamonds. For lab-grown diamonds, like CVD lab-grown diamond, many of them show brown color, as we mentioned at the beginning. After HPHD treatment, the brown color could be removed. So it is very often we see in the trade that a CVD diamond was HPHD annealed to remove the brown color. Here's basically some summary of the major CVD color of a diamond with some additional post-growth treatment. HPHD annealing could turn some CVD diamond to yellow color, very similar to KB yellow, and it could be irradiated to blue, different saturation of a blue color. But if they are HPHD annealed plus irradiation annealing, we can generate a different type of saturations of a pink color in CVD diamond. This is pretty often, quite often, we can see this type of treated CVD diamond in the trade. And the treatment can also be applied to HPHD synthetic diamond, HPHD lab-grown diamonds. The 3 diamonds I show here, they are all HPHD lab-grown diamonds that irradiated and annealed, of course, very important to start with a suitable concentration of isonitrogen, irradiated, annealed, and attend to a different type of a saturation of pink color. This is one of quite a special diamond that we see in the laboratory is the orange color. It's orange color, beautiful orange color is not a very often. To introduce orange color is really difficult. This is a HPHD lab-grown diamond, sort of very nice. It's a vivid orangey pink with a pretty strong orange hue, and that is over 5 carat. It's very nice. To us, it's rare to see a HPHD lab-grown diamond can be treated to show strong orange color. So now we know there are quite a lot of lab-grown diamonds in the trade, and meaning is that quite often some of them is applied with a post-growth treatment. What I show here is just it's a very well-known diamond producer in China called a sinocrystal diamond that produces a lot of many HPHD synthetic and larger stones. This just to show you the wide range of color they are experimentally introducing to their product. And it's a pretty wide range of different saturations of pink, yellow, blue, and some weaving with a green color. So I believe we'll see more and more color-treated lab-grown diamonds in the trade. Since the top quality natural diamond of colors are very rare, and we know different type of technologies are applied to very effectively to modify the color of the diamond, some including both natural and lab-grown diamonds. It basically diversify our trade, introduced more products options for the trade. All of the products are legitimate products. There's nothing wrong with this treatment, but it's very important to separate these treated colors from naturally colored diamond, because otherwise we're going to lose the consumer confidence with this product. And if we have no confidence, consumer confidence with diamond, there will be no diamond industry. How do we separate naturally colored diamond from these treated ones? Basically, we heavily rely upon, again, on the defects. It will be very easy if we can find some defects that only occurs, find some defects that only occur in either natural or in treated. That'll be very easy for us to do it. Actually, it is much more challenging than that. Almost all defects that could occur in both natural and treated stones. So there's no simple way to separate these two groups. We basically rely upon the defect configurations in a diamond that would include the species, like what type of defects occur in a diamond, their concentration, their coexistence, what stay together, and their distribution. Distribution is very important as well. Based on this information, we try to separate a naturally colored diamond from a treated one. The technology could be simple, and gemological observations still very, very important for us. And it could include like even the surface burns and inclusions, strain fluorescence, phosphorescence, and some observable color distribution and fluorescence image. These are still very useful technology for us in the laboratory to identify treated color diamond. But it is almost impossible to use a simple gemological method to confidently identify every single treated diamond. The spectroscopy technologies is getting more and more important. Here, just list a few of the main technologies we're using in GIA. This technology, the list is getting longer and longer over the last 10, 20 years. including infrared absorption, UV visible absorption, photoluminescence spectroscopy is getting very important, and with all types of different laser excitations from UV to infrared region. We even have in GIA now have an EPR technology, have a luminescence image, as well as a spectroscopy technologies. With all of these technologies we are using, and I would like to say in GIA, we are quite confident we can identify vast majority of treated color diamond, either natural or synthetic. Yes, of course, we can identify all of them, but for natural stones color treated, we can identify vast majority of them. I don't think GIA ever say we can identify every single diamond that is natural diamond that is a color treated. We just say we can identify a vast majority. That's slightly different from what we claimed with the synthetic diamond. We basically believe we can identify every single laboratory grown or synthetic diamonds. So that's what still some challenges even after very long research and investment in this area. I know there are some challenges, probably some unhappy client who use our service for fancy color diamond, because for very few green blue diamond, due to irradiation, we still occasionally, very occasionally, we give undetermined color origin core. So I understand it's very frustrating for the client when they get a diamond with an undetermined color origin core. That could be very frustrating. The reason behind that is what I try to show here is a small diamond mine in Brazil. We visited last year. The total amount of production is very, very limited. The small diamond mine, open mining, but they produce some beautiful blue diamonds or greenish blue diamond. This one, the lower left image, it is I would call it a non-natural green diamond from Brazil. And in the right-hand side is a non-artificially irradiated green-blue diamond that color is due to artificial treatment. Sometimes, not always, it is very difficult to separate both if we don't know the history of these stones, because these two diamonds basically are colored by similar physics. One irradiation process happening in nature, another irradiation process happening in the laboratory. With the current available technology, it is very hard to be 100% confident to separate both of them. Many of them we can separate them, but to separate 100% of them, there are still some challenges. This is an area that GIA is probably the biggest issues we have in the laboratory, how we can confidently identify this irradiation related green-blue diamond to minimize the overlap natural from treated ones is still the biggest challenge we have. GIA is investing very heavily and put a lot of research in this area, try to keep improving our identification criteria. Here's as a last slide, I just want to show Mr. Khurana Shield. He's a pioneer in GIA identification area and worked in GIA nuclei for a long time. I just want to emphasize, even in 1950s, he find that an irradiated and annealed yellow diamond would show a special absorption line, use a desktop scope at 594. So he used that to separate a naturally irradiated from artificially irradiated yellow diamond from a naturally colored yellow diamond. So this type of effort we will continue and continue to improve our identification criteria. Hopefully we can identify more and more irradiation related green and blue diamonds and to reduce the stress of the blade. With that, I would like to finish my talk by here, and thank you very much for your attention. I was happy to answer your questions.
Thank you so much, Wuyi. you know, it was actually recently Mr. Khurana Shield's birthday. I think it was late last week. So it would have been his birthday. So it's a nice little shout out to him. So we have some good questions. We can go ahead and jump into it. So what is the reason a diamond is dark and vivid in color and another diamond is light in tone? What causes the tone differences in color?
Well, I think basically it's if a cut contributes to the final color, but in general, the most important thing is the concentration of the specific defects that are responsible for that color. Let's say we have again, just keep in mind, it's very important the cut contributes a lot to the face-off color of the diamond. But let's say if you have two diamonds, they have exactly same size, same cut. One is that they both have different tones, and the main reason of contribute to the difference is the concentration of the defects. But the concentration of the defects concentration is very low overall, that in the ppb level, in the ppm level.
Okay. What makes a green diamond green? And so, like, what is the chemical that makes that green?
No, I can give you quite a few reasons that can cause green color in a diamond. First, it could be vacancy. Let's say a diamond with some brownish color, with some yellowish color is very often in natural diamond. If this diamond is irradiated, either naturally irradiated or irradiated in the laboratory artificially, this diamond will be turned to green. So this is the main reason for the green color. Second, it could be due to fluorescence. We talk about absorption. Absorption is the most important thing that creates the color of a diamond. But for some diamonds, let's say if a diamond has a reasonable amount of H3 defect and has a very low concentration of A center in the diamond, this diamond, or a reasonably low concentration of A center of nitrogen in this diamond, the H3 could fluorescence. In addition to absorption, the H3 defect in this diamond could fluorescence. H3 fluorescence green. So that will be a green color due to fluorescence. There's a second reason for green color. The third reason could be related to the hydrogen defects in diamond. We still don't know exactly what it is. The exact physical model of the defects, we don't know, but we believe some hydrogen could contribute. A hydrogen-rich diamond could show some green color. So we believe that could be hydrogen-related defects, is the third one. The fourth one is H2. H2 is a defect in the infrared region, but that absorption could extend to the visible light, could absorb a decent amount of a red or orange and create the green color. So in the presentation, I show you a treated diamond with green color due to H2. That is the fourth reason. The fifth color region for green, I showed you a couple of pictures of a chameleon diamond that show a pretty clear green body color of the chameleon diamond. What is responsible for that green, we don't know. But exactly the physical model, we don't know. But that could be another reason of a green color. The sixth one, if I keep going on, this is a green color, could be nickel. And nickel is a very common defect in diamond, in natural diamond, and in HPHD synthetic diamond. Some natural green diamond is attributed to the nickel defect in this natural diamonds. So I talk about a 6, and there could be a couple more very minor but not a major defects that could also create some green colors. So just on this. So then,
oh, sorry. So then how can we determine if a green diamond is natural irradiation or has been treated through irradiation?
It is a very, very difficult issue. So we talk about the defects combination, like what are defects in addition to the vacancy, what else occur together. Then this other defect not necessarily have anything to do with the color itself, and not if it doesn't absorb visible light, it has nothing to do with the color, but what other defects occur together and how they're distributed, because a treatment, not artificial treatment, could create some quite a clear difference from a natural irradiation, how they distribute. So these are, I would believe, the major factors we need to consider to separate the natural from treated ones. But that doesn't necessarily say we have the full confidence that we can identify every single of them. But that's the basic principle. I think that continue to be valid for the future to guide us how to keep improving our criteria.
Okay. Can we get yellow colored diamonds through irradiation?
Yes, it is quite often applied to create a yellow color. I would say if we have a diamond that is a very light yellow, it is, let's say, STUV color, and it's type 1A diamond. That type 1A means it has quite a lot of nitrogen. This stone can be quite easily turned to any saturation of yellow you want. You just put an irradiation, put it under the electron beam, and then heat it up. Then the stone will add more yellow to the pre-existing yellow. So that just depends on how yellow you want to be. Control the treatment conditions. A stone will change to whatever yellow you want.
And so if a diamond is treated with irradiation, do they ever lose their color, or is it permanent?
With the technology I was discussing today with the irradiation, HPHD, or combination of multiple treatment, we would call this a permanent color treatment. Color will not change. The color will not disappear over time. But what I'm saying, this is not necessarily mean color is 100% stable. The color could still be unstable. Let's say a diamond colored by NV centers. If you expose this diamond to strong UV, it may build up some orange color or some even brown color. It's not very stable, but it is reversible. After a short period of time, the color will come back. So it is a permanent color change. For most of them, they are very stable. For example, the yellow color will be very stable, but for a few of them, color may not be stable, but will be reversible. It will come back to what it's supposed to be.
Okay. Do natural red diamonds only come in small sizes, and why are they so rare?
Yes, in general, we don't see very big natural red diamond. I forgot the exact size, about a 5-6 carat. The famous red diamond from Africa. That's about 5 carat or 6 carat. Red or pink color we taught today can be attributed to defects, 550 band and NV centers. NV center, I don't think it will ever create a red color grading for a natural diamond. It can generate a red color for a treated one, or treated natural, treated synthetic, but we will never find a natural red diamond colored by NV centers. So first, I want to try to emphasize the natural red color diamond is basically colored by 550 band. 550 band defect is something we don't know the physics entirely, but to some degree, we believe it is related to dislocation or plastic deformation of a diamond. That means it's a diamond experienced over the long geological history some plastic deformation, either during the transportation process or even after the crystallization in the deep part of the earth. The plastic deformation created a lot of damage of the diamond itself, including fractures. For example, if you look at the Argyle diamond, rough diamond, there are a lot of fractures. And that is probably the main reason why we don't see very big red diamond, because they are plastic formed and they're very easy to break over the natural process.
Okay, so someone asked the question, there are several beautiful octahedra for colorless diamonds, but few to none in colored diamonds. So is it related to, you know, the shape of rough diamonds for colored versus colorless? Is that related to what you just mentioned with red diamonds?
Well, yes, there are some almost beautiful octahedron crystals of a diamond. They are colorless. For example, if you're familiar with the diamond from Siberia, yeah, they have some beautiful stone like that. But this diamond still have a lot of nitrogen in this oxygen diamonds. They are type 1A diamond, but the nitrogen just aggregated in this perfect way that the nitrogen in the aggregated form, they don't absorb visible light, so it's colorless. On the other hand, I think the top quality natural colorless diamond, many of them are type 2 diamond. So they have no nitrogen or no detectable nitrogen in these stones. These stones usually don't show the beautiful oxygen shape. Actually, natural 2A diamond almost exclusively show the irregular shape. That's just a natural process. And if you have interest in go deeper with this topic and just read Evan Smith's the publications, he has been doing a lot of good, very impressive research about the natural type 2A diamond, the clipper diamond, how they formed from transition zone, lower mantle, and why. That answers many, many questions about the color and their morphology.
Great. Is the ID100 capable of separating color-treated natural from color-treated lab-grown diamonds?
Good question. Let me think a little bit. So ID100 right now with updated software, we are able to use it to separate natural diamond from synthetic or laboratory grown diamond with fancy colors. And for pink in particular, we're talking about it can separate natural starting material treated from synthetic material treated. So for pink, yes, the ID100 would be able to separate a natural pink. We'll pass that, and we'll refer treated synthetic, and also we can separate treated natural diamond, but now with additional pink introduced.
Great, and ID100 is available at store.gi.edu if you want to learn more about the product. We have some videos there. And so does the GIA lab see laboratory grown diamonds with purplish pink color grades, especially in a low saturation like a fancy light?
Yes, it is very often for a treated pink diamond with some purplish hue. Yes, we saw some.
Okay. Why do treated natural diamonds change with heat, but HPHD diamonds do not? So
the question is why treated natural diamonds will change color with heat,
yes,
but not HPHD synthetic? Well, I don't know what exactly the question means. Let's say if we have a natural diamond irradiated, right, it is either blue or green color. If we talk about a heating after irradiation, yes, the color will turn to yellow or orange color for type 1A diamond, or even for type 1B diamond turn to pink. That reason of the color change is due to the vacancy introduced after irradiation will start moving. It is diffused through the diamond crystal, and the vacancy will combine with the other defect, with the nitrogen either in the pair form or in the isolated form, at a form that generate a different type of defects that could be H3, H4, or NV centers that dramatically entirely change the color of the diamond after irradiation. For HPH, for synthetic diamond, actually the same principle applies. Same thing, if, let's say, I just use an example to answer your question. Let's say it's a very subtle yellow synthetic diamond, either HPHD synthetic or CVD synthetic with some isotope nitrogen. Immediately after irradiation, it could be still green color or bluish green, greenish blue color. That's a stable color if we don't hit it. But if this diamond is heated as what we did to the natural diamond, yeah, these stones will all turn to a pink color. So it depends on how you define the heat and the heat temperature and also starting material. And the color will change for both natural and synthetic.
Okay, great. Okay, 2 more questions. Are stones usually treated before or after they're cut?
In early days, I think every HPHD treatment is cut first and then treat and then cut again, so they're gonna lose more weight. I think HPHD treatment now almost exclusively is they treated performed basically half finished and HPHD treated and then polished once. That's for HPHD treatment. For irradiation, it doesn't really matter because the technology is good enough for irradiation treatment without any technically there's no damage to a faceted diamond after the treatment. So there's no repolishing is required for irradiation treatment. I think a lot of irradiation treatment happens to fully faceted diamond.
Okay. And last one, can a powerful microscope, like an electron microscope, let us actually see the carbon atoms and if there are any defects?
Well, yes, to use in the really, really good, excellent TM transmission electron microscope, technically we can see atom. I'm not sure we can see one defect to that resolution in the TM, but that means we need to damage the sample. The sample has to be fabricated to a very, very thin, very tiny sample before we can put it into the TM to see it. So that is a method for research to see the atoms in a crystal, but in the gem lab for identification purpose, that is prohibitively expensive and also is not applicable technology for gem material because we cannot damage any of our gemstones.
Great. Well, thank you so much for joining us. This is great information. If you have any other questions, please join us on Instagram, Facebook, LinkedIn, and Twitter. Thank you for everyone who attended, and thank you so much, Wuyi. Join us again next week where we'll be here with Dr. Wim Vertriest for Geology 101 for Gemologists, where he'll explain all the natural processes that form colored gemstones. So thank you, everyone.